Welcome everyone. I'm here with some of the people that have been working on building the orb over the past few years. And I thought we would just take a little stroll through the code base and kind of try to understand how everything works, see if there's any cool, interesting things that we can learn about it, get up to speed with it basically. So why don't you guys go ahead and introduce yourselves?
I'm Dan. I lead the software team for the orb, which is roughly 10 people right now.
I'm Anastasios, part of the same team with Dan. I'm a staff engineer working on the software that actually builds and makes the orb working. And Valentin?
I'm Valentin. I'm also a part of this team. I lead the development of Orb Core.
And I'm Miguel. I'm not from the orb team, and I haven't really looked at this code base before, so hopefully through this video, these guys can help me and you understand it.
So this orb is running Orb Core, which is the main repo we're going to talk about today. It's the main process that runs on the orb and is responsible for all the main functionality. Just to set the context before we jump into the code, we should remind everyone what the orb does and the requirements then transfer to the code. The first thing, of course, is that all of the images that the orb takes are processed locally and don't need to be sent to any backend for processing. This is very important for privacy and not needing to trust some arbitrary backend. Of course, for that to work and for other reasons, we need the orb to be very secure. If somebody could get their own code running on the orb or tamper it in some way, the main purpose of the orb wouldn't work. We also are optimizing the orb to be as verifiable as possible. So the code we're open sourcing today, eventually you'll be able to check that an orb is running exactly that code and it wasn't modified. That's also very important for decentralization. Finally, it has to be easy. Like it can't be that you have to, put your eyes up against a certain device or have any specific technical experience to use the orb, because this is supposed to be universal and deployed everywhere.
Should we describe a little bit then the architecture and some basic principles on how we designed this piece of software? Just to give an overview, at a very high level, this IoT device is actually running on just standard Linux with a lot of custom drivers and a lot of custom software that we build ourselves. But except this specific part is like a very normal Linux machine most people would be familiar with. So we don't have to do something really, really extreme or something very unique here. But the heart of this device is what we call the Orb Core, that we are very happy to release also open source. At a very high level, again, this piece of software, Orb Core, is segmented in a lot of small agents that they are controlling various parts of the orb while a sign-up is happening. Valentin probably would be the right person to give like a very high-level overview of how these agents are working. But I think the most important part we want to highlight here is that it's an interesting architectural piece of software that is very, very performant, and we really care about performance. Valentin, do you want to talk a little bit about the agents and give a very general overview with a broker in the middle and how these are communicating?
Orb Core uses star-shaped architecture with agents at the outside and a broker in the center. Agents are not interconnected. They are connected only to the broker, and they all run concurrently. They can run on Tokio tests, OS threads, or separate OS processes for extra isolation. But they all communicate with the broker via bidirectional channels. Agents can't communicate with each other. They communicate only with the broker, and the broker runs no other logic. It just routes messages from one agent to another, possibly broadcasting to multiple agents. Here on the screen, you can see a big list of agents. They are not active all of the time. They are enabled and disabled as needed, depending on the current place of the sign-up.
To make sure I understood that correctly, the way that this code base is structured, there's a bunch of different services, maybe the camera, maybe a depth sensor, maybe just like some service that uploads images or the AI models. And all of those little services are structured into an architecture that we're calling agents. The job of the main code base is just going to be to route messages between those and just like pass signals, enable and disable it, but not really have much logic separate from that.
Yeah, there's like a central, high performance broker in the middle that just receives and sends messages to all these agents.
The logic is all in the agents, and the broker just like takes care of like routing those things.
Except for the plans, which is the next step.
The plans are the heart. There's something to highlight here that is quite important, is that we have like 3 different types of agents that is very important to distinguish. We have processes, that they are separate processes, that they are isolated, and this is for security and privacy and also reliability. But then we have also agents that they are threads for performance, especially the ones that are very sensitive to latency. And then we also have asynchronous tasks that they work on top of TOQRS, which is also another interesting primitive that we use.
So we have the agents, we have all the synchronous tasks.
Yes.
Let's maybe go to Orb Core so we can see like how it gets bootstrapped and everything gets initialized.
Yes, we have the agents in the middle, and the other quite important primitive, it's the plans. I'm going to just browse through the master plan, which is the one that governs a whole signup from the start to the end. So when someone wants to write some piece of functionality on Orb Core, it needs to define one of these plans. That these plans, they just execute on Orb Core, and then all the information they're coming through the broker, they're just routed on the right places, or they're consumed from the right places to execute the logic you want to do. So for us, the master plan, for example, is exactly during a sign-up what is actually happening.
So this master plan basically is like the entire list of instruction that like leads to a sign.
Yes. And I'm just highlighting here literally the 2 most important steps during this master plan, which is how do we actually do a sign-up and what is happening after a sign-up is done, for cleanup, information, and some maintenance things that you have to do to prepare the orb for the next signup that's coming in. And maybe we can dive a little bit bigger to the do signup. You can see, for example, here that we are scanning for the QR codes that we expect from the user to give us. And then we have 2 big important parts, the biometric capture, when actually a user sits in front of the orb and we scan the biometrics. And then we have the biometric pipeline, which is actually the part that we are checking that everything works properly, fraud detection, the images have all the quality that we require and things like that. At the very end, we have the actual enrollment and the self-custody, which is actually a feature that we are going to release pretty soon, and we're quite excited about that. When the enrollment is done, you have your sign up and you're very happy World ID user.
Verified World ID.
Verified World ID user.
Now that we've gone through like the basics of the flow, maybe we could look at it a little more in detail, seeing more of these like magic steps for like the pipeline capture and the pipeline processing. Those seem like the most interesting parts. So we probably want to look at those and try to get an idea of how they work.
Just as an example, to dive a little bit deeper on the details, let's go into actually how we perform a sign up. And we're going to show how we just check before a sign up starts that we detect the face so we can start the actual sign up. As we said, this is the master plan that all the main logic goes through. And we said that, the first step is the biometric capture. So if we literally just go inside the biometric capture, we can find as literally the first step if we detect the face or not. And if we go again deeper into this, we're going to see that we have another plan inside the plan. Because again, as we said, this primitive of plans is a very important concept to the Orb Core. And this is how you segregate and you organize pieces of logic. So let's actually go inside this plan to see what exactly is happening. And the first thing that we can actually see here is that this is how we control the hardware itself. These are the agents that we ask them to start, enable, get ready, be warmed up to give us information. And then the important thing is that a plan is a reactive structure, if I may say, that we are handling information that are coming to us. So for example, here you can see that the detect face plan is handling input from one of our AI models, the RGBNet. And here we are checking if actually there's any prediction from the actual neural net if we detect the face. And if that's the case, then we are ready to move on and disable and stop the RGB camera because we are done and return back to our original piece of code to continue on to whatever comes next.
Maybe it's interesting to discuss how plans and brokers interact, because we talked about brokers routing information between agents, and we also talked about plans kind of controlling information between agents reactively. And I think the interface between plans and brokers is then very interesting. So maybe let's go back to the face detection plan.
So here is a face detection plan. It's one of the simplest plans, and it's a good example to show how plans work. So a plan is an object which injects into a broker. A plan implements the plan trait. The plan trait consists of various handlers for agents. One plan can implement a subset of handlers because by default, all handlers in the plan trait are empty. So this plan is interested only in the RGBNet agent. It processes the output of the agent and returns the broker flow object, which can be either break or continue. Like so, if we go to the run method of this plan, we can see that the orb argument is the broker. We prepare the broker, we enable the agent that we need, then we call the run method of the broker. The run method exits one of the handlers, returns broker flow break. Then the plan initializes the agent and returns the actual result to the caller.
So basically, if I understand correctly, plan itself is an interface that provides optional handlers for every single piece of functionality in the orb. So every AI model, every sensor, etc. And then when you're implementing a plan, what you do is for some of these sensors that you might be interested in, like for example, the RGB camera in this one, you will implement the function and that lets you interact with the RGB camera. So then when you're running the plan, what it will do is it will go through every single handler. By default, I'm guessing they all just like say continue. When you find one that actually has logic that you have overridden for this plan, which is separate from the default do nothing, then it will handle that logic. And eventually, while you're working that logic, maybe if it's an AI model, you want to have it run over and over until it detects a phase. When you detect a phase, you tell it, okay, we got what we wanted. And then it breaks and you can keep going through the code in the run function.
This is actually the trait of the plan. You can see that we have handlers for pretty much everything that is running on the orb. The RGB camera, the thermal camera, the various neural networks that we have, the meters, the QR code, and actually what you do, you implement the plan against this trait. And exactly how Valentin said, you just control the flow if you want to stop or if you want to continue to get more information for another try for all of this.
The broker has multiple handler methods for each agent. For example, here is the handler for the RGB camera. It routes the output of the RGB camera agent to QR code agent, Roku code agent, RGBNet, but only if these agents are enabled. And as the last step, it calls the plan implementation of the handler. So this way, a plan can inject into the broker.
Yeah, and so this would basically be equivalent if we didn't have this, would be to have to manually start the sensor, do things, stop the sensor. And this basically lets you much simply tell the plan, here's the things that we care about. We have custom functionality for those. All of the other sensors, when this system calls those sensors, it will immediately continue because we don't have any logic there. And so it's just like a nice abstraction that lets us clean up the code a little bit.
And keep everything fast.
Yes.
Most importantly, yes. After the orb understands that there is a face in front of it, the next step is actually to find your eyes so we can steer the mirror that we have inside the orb to get a very clear picture of your iris. So then we can process it. And here you can actually see that there's another plan that is doing all the magic. And this is a far more complex plan than the previous one that we see, and has a lot of things that it needs to handle to make sure that we are ready to start capturing your iris. Just before we start, the actual capturing of the irises, we have to do a lot of hardware setup through all of our detectors and sensors. And then we see exactly the same pattern that we are handling inputs that are coming from now 3 different places that we care: the face identifier, the RGB net, and the IR net. Let's say each one of them are responsible to give us a very clear picture on where we should be targeting our hardware, and then assess if the information that we capture from our cameras are good enough for us to do processing on a later stage. And actually, you can very clearly see here that we are assessing the score of the iris that we're capturing, and we're striving to at least reach a specific threshold of clear quality, and then we progress further. Another interesting thing is the fact that we need to capture 2 eyes, so we need to have a way to separate when we are done. So you first need to capture one of your eye, then the second one, and then at the third stage, you need to capture your face, because that's also part of the self-custody. So again, we see another emerging property inside plans, that we have objectives internally that we need to hit on every iteration.
It's maybe interesting to note here that parts of the code that are open source just recently are staging grounds for features that are not actually yet deployed to World App. And so here you're seeing, for example, checks that ensure the face quality is very high, and that's for future features that have been announced for World App but are not yet deployed.
So we're giving you a sneak peek of this.
It's a sneak peek.
To summarize really quickly, the very, very basic logic of this plan would be to move the mirror so that it points to your eyes, then get a really high-resolution photo of one of your eyes, make sure that it's high quality enough so that we can work on it, then switch to doing the same with the second eye. And then once we have both of these pictures, we just return back and we continue the logic separately, right?
That's correct.
Nice.
And it's mentioned in the blog post, but a very critical step here we just didn't mention yet is the autofocus. So it's not just steering the mirrors, but then once the mirror finds the eye, there's a separate feedback controller which adjusts the liquid lens to find a sharp image.
Nice.
And all of this is then scored by a real-time neural network that the AI team built for us. And that's custom for us to find sharp irises. It's not some off-the-shelf component.
And all of this happens fairly quickly, right?
Yeah, we'll show a video at the end.
Nice.
Again, just to go back, there's a lot of housekeeping that we do, obviously, after each capture that we do. Just also for us to have a feedback loop for ourselves, how the hardware is performing and how, all the parts of our system are properly done. Then the next step is actually the biometric pipeline, which is another interesting piece of our big plan. Again, organized in a separate plan by itself. We see the same pattern here. And if we dive again deeper into this, we will see here that we have a lot of AI agents and a lot of information that they're conveyed from them. So we can assess if the capture that we did is good enough for this to be a proper sign-up before we submit your sign-up candidacy on our backend.
Is this plan mostly taking care of validating, or is it also where you generate the iris code? Does it happen later? Is it here?
It generates the iris code. That's one of the core things it does. And that uses the iris model, which has also been open source.
Maybe one thing that I think is interesting for the people that are going to work on our code base is the fact that we have the agents, that they are separate pieces of software that you can independently execute. But sometimes it makes sense for you to merge some of your functionality under one agent and create one small monolithic design. Mm-hmm. And the reason I'm highlighting this is because one of the big things that we did for OrbCore, and again, this is part of the open source release, is that we give you a nice abstraction for Python agents, and OrbCore is very keen on connecting with Python. So one of the things that we've seen in the past to be a bottleneck is sometimes that you might want to run a lot of different pieces of Python software, and because the Python interpreter can be quite heavyweight in memory, we give some abstractions that we can have one Python interpreter that is running a lot of different pieces of software all together. And we call this a mega agent design because it's one agent that has a lot of responsibilities, hence the name mega agent.
This might be a good time to dive into the interface because it went through several iterations and is probably unique to our code base. Also a good time to maybe mention that several of the agents that are part of the biometric pipeline are not included in the open source software. And that's because they handle fraud processing and we're working to make the interface to those agents explicit in the open source software. In the first release, they're just removed. And we're also working on sandboxing them so that you can prove from the open source software to a reasonable degree that those agents cannot, for example, save an image to disk or upload them.
An agent can implement one of the three agent traits. It can be agent task, agent thread, and agent process. Agent task runs on top of Tokio. Agent thread runs on a dedicated OS thread, and agent process runs in a completely isolated process. The main difference between those traits is the run method. You can see that in the agent task, it is asynchronous. So if we run asynchronous code, it's better to use agent task because it's a most lightweight agent. If we need to run synchronous code inside an agent, then we can use agent thread. For example, if we have a synchronous API for some hardware, and we can use agent process if we want extra isolation. Mainly it is for security and reliability, because even if the external process crashes with segfault, we can seamlessly restart it. Optionally, we can retry the latest message passed into the agent. We use this for some of the agents which are not that reliable.
What I'm getting from this is that, like, within agents, there's 3 different ways to run it, which are represented by different interface. For async agents, those are mostly just run through Tokio, and then there is a method for sync agents that are just run on a separate thread. And then there's a third method for agents that are maybe more unreliable, that need isolation, or that can crash, where you just like run it on a different process, and that gives you access to some extra options for recovery.
Yep. And the one thing I want to highlight is actually how we communicate exactly with these agents. Because obviously for the tasks and the thread agents, because the communication is local, it can be very, very performant. But unfortunately, if you have to choose the process agent, you have to go through a serialization deserialization process, because because you have to communicate through a different whole process. And to do this, we are giving you some very interesting primitives. We call them port. And the idea here is that we have chosen to use shared memory as the way to communicate cross processes. I mean, there are a lot of other ways to do it, but the shared memory one is the most performant one, because sometimes you have to move a lot of information between agents. And we give you this out of the box using the Archive library that is a very low cost serialization and deserialization framework for you to transfer data across our processes.
Yeah, it's zero copy serialization framework.
Maybe it makes sense then to look at one of the Python agents and show how we use PyOxide, which is another library we're very grateful.
On top of this, now we have built some other abstractions because, for example, as I said, OrbCore is very keen on working with Python or, enabling our AI teams to write code in the way that they have used to. We're not trying to impose any languages specifically. We try to be versatile. And here we have a Python agent that actually you can see is built on top of a process agent. And that gives you some more interesting abstractions on how you can communicate with Python more efficiently. And we are going to dive a little bit deeper on how the Iris Python agent works, because Iris is also open source. So here you can see that this iterate function is one of the most important parts of an agent. This is how you control the agent. This is how you send information to the agent from OrbCore to execute some kind of functionality. And here you can see that we are sending an estimate request. So for a specific frame, and if it's a left or a right eye, we are asking the AI model to tell us information about the specific frame, if it is good enough, if it can be interpreted, and if the Iris model can create an Iris code. And here you can see that we start recognizing some Python patterns. They're coming from libraries like NumPy, PyO3. And here you can see, for example, that For the agent, which is the Python interpreter, we are calling a specific Python method with the arguments we want to pass. And that's the way that we are asking Python to do something for us. This is how we delegate some computation to Python. And then the interesting thing is that we need to build the right typing system to get information from Python back to Rust. We have a lot of code examples on how these are happening, but I'm just going to show you really quickly. This is, for example, the output of a specific function call that we do on Iris. And if you want to write your own Python agents, it's actually quite simple because there are a lot of annotations that are coming directly from PyO3 for you to build all the abstractions and the data types you require.
It might be a good time to also mention that some of these agents are in the process of being ported to a pure Rust implementation, and that has seen significant performance improvements to the biometric processing phase.
Kind of a funny story because we're trying to introduce Rust, but on the other side, we don't want to completely change the workflow of the AI teams. So we are having Rust calling Python that again calls Rust and coming back from Python and Rust.
Nice. And that is still more performant than just doing things in Python. 200
times more performant, actually.
That's crazy.
Okay, so we talked about the Python agents and how we can make requests to our AI models. So now we go back a little bit higher again, back to the biometric pipeline. The same pattern applies to all of this information that we would like, to analyze. So at the very end, if the biometric pipeline finishes successfully, then we go back to check actually that we didn't detect any fraudulent behavior. Again, I would like to highlight that the Orb is one of the most private devices out there. So we strive for maximum local computation to anything that has to do with fraud. So exactly after the biometric pipeline is finishing, we do some checks to see if everything is okay. Something to highlight, for obvious security reasons, we are not releasing exactly the checks that we do locally. So for the open source version, this is going to be just the engine itself that other people can, implement their own checks, but we're not releasing the ones we do currently. And the last piece is that after we do these checks, the only thing that remains is pretty much the enrollment of the user. And we can actually go a little bit deeper here to see what kind of information we provide to our backend. I'm going to go inside the plan again, the same pattern to show you the request, the sign up request that we do. And you will see that the information that we are uploading is only the important part that they required.
Here you see the list of all the fields that are included in the enrollment request. This is the main request that happens after a successful capture. The images have been processed. We now know if there's fraud or not. We have high quality images that we need. And the pipeline stage has generated the iris encoding, which here is called codes. Everything else in here is metadata. So it includes the QR codes, the information that was in the QR codes shown from the user's phone to the Orb. It has metadata about the software version that's running on the Orb. And it critically has a signature field. This is a signature of the iris codes that is generated by the secure element on the device. And we can look at what's exactly signed in a second. And finally, it has a sign up reason. This is because even if we detect fraud, we want to submit this enrollment request for our own purposes. And so sometimes, even if we don't want to enroll an iris code for the uniqueness service, because local fraud was detected, this request is actually still sent.
So this is the part where the Orb will take all the data that it generated and it will sign it so we can have some certainty that someone didn't just send it to our backend, but it actually went through the process of the Orb.
That's right. And so this is one of the most critical steps from a security perspective. And that's why we actually don't do the signing on the main processor in the Orb, but we have a separate chip which has a more secure method for storing private keys and doing the signing. So we take the iris code, which you see here in the form of I left iris code. The mask code is related to the iris code. It tells us which bits of the iris code should be ignored because they're occluded. For example, if you have hair in front of your eye, We have some metadata about the versions of the relevant models that's important to match to the Iris code. And we have the content of the user's QR code, which is part of how the Iris code gets matched to an identity commitment, which is stored in the Merkle tree on the L2. Of course, the ID of the orb. So all of that information gets hashed and sent to the secure element. The signature comes back to the main processor, and that signature is included in their enrollment request, and it is always used if you need to validate, for example, later on the user's device, that this Iris code came from an orb.
And one just last piece of information that maybe would be nice to have is that also the broker is not a primitive that needs to be the one and unique only broker. We have actually multiple brokers to monitor different things. So again, to separate responsibilities between, let's say, the hardware and let's say some monitoring facilities that we have. So in that way, the design can be extremely flexible for you if you want to build like different capabilities.
Maybe we should also mention kind of the key parts of the code that we hope will be useful for other projects and that can use more work to be factored out of this code base into separate libraries. So I think maybe the most interesting to others will be the agent framework, which we spent some time on discussing, the Python interface.
I think the broker, the agents are the two most high-level things that you can build arbitrary stuff on top. But maybe the ones that we also would like to see some maybe innovation externally from us would be, I don't know, fraud detection methods or, more efficiencies around how we communicate with the agents and how we serialize the serialized data, or supports of other different kind of hardware devices. That would be something that we'll be extremely interested in.
To kind of like summarize a little bit of what I understood from this, and you guys tell me if I got anything wrong. The way that the code base is architecture, there's two kind of like big primitives. There's the broker and agents, which is basically a system where every single piece of sensors, functionality, AI models has its own agent that encapsulates the functionality. And then there's a broker that will take care of calling in, calling out, enabling them, disabling them. And then a plan has access to the broker, and it's kind of the way that you encapsulate information. So you have, for example, the plan takes care of the making sure there's a face, and that will take care of enabling the RGB camera, then has some logic for handling the RGB camera and the AI model, and then returns. And so these plans are a way to encapsulate and get rid of a lot of duplicated code for enabling and disabling things that you may want to do in multiple separate things.
We're using code, keeping things fast by leveraging async. And we didn't talk about this, but it does help with testability as well.
Nice. Yeah, because I would imagine that you can write tests for all of these agents separately.
Nice.
You're ready to join us in OrbCore,
Yeah.
Jel?
Yeah, I can get started contributing now.
We're hiring.
Okay, so now that we've seen how the code works, maybe we can try to actually see it in real life and do a sign up.
Let's do it.
So we do have a staging system because obviously the thing with the orbs is you can only sign up once. So
That's
it wouldn't be very useful to test if you could only ever test once. Someone had to like go outside and find someone that hasn't
That's right.
yet.
Well, even on staging, it's seen me before. So we don't test on prod.
So we're using staging here.
That's right. So this orb is in the idle mode. You press the button to start a sign up. Then it goes into the QR code capture mode. First is the operator's QR to unlock the device. Then the user generates a QR in their world app, and that's shown to the orb. Then it goes to the biometric capture phase, where you look into the orb. Once that's done, it goes into the processing phase, which takes a few seconds here. This is doing the iris encoding, fraud checks, and then the upload for both the self-custody package and the enrollment request, which is the signed iris code.
The verification was not successful.
This orb has seen me before, of course.
Thanks so much for watching, everyone. If you want more details about how the orb works, how the iris works, there's plenty of content very in-depth and very out-of-depth in our blog that we can look into to learn more about the process, learn more about WorldCoin, learn about where you can go sign up with an orb, all those things. You will also be able to find somewhere, depending on where you're watching this, a link to the code base that we just reviewed that you should be able to look through. And I'll also do my best to link to the specific parts that we're talking about in the video. And once again, thanks for watching. If you have any questions, feel free to tweet at us. And we're also hiring if you want to contribute to the repo and also get paid to do it. If you really like working in Rust, this is probably one of the most exciting Rust projects that you could be working on with a real world impact. So that's great. I don't know if you guys want to add anything else to that.
There's a few other repos that we open source today that complement Orb Core. And so feel free to look at those as well, most in Rust and some in C. And then, of course, I want to thank the team behind this. So there's a lot of people that aren't on camera right now. Valentin was one of the earliest and built a lot of what you've seen today. Anastasios came a bit later and helped especially with the AI models. And the AI team is kind of the brains behind all of those models, making the iris encoding and fraud detection work. And we showed the interface to those, but not exactly the code.
Yeah, there's obviously a lot more that goes on. And we also standard show some giants also in all of the Pio 3 library that we use in Rapid Python, all of the other dependencies that we use, Tokyo,
Linux.
Yeah.
Exciting times.
Very excited times. Once again, thanks for watching. And make sure to check out the code base, check out the articles, maybe get signed up for WorldCoin, all that. And we hope to see you soon. Bye.